Good morning, everyone. Now we have a change of subject. So we basically went through all emission processes that are characterized by or produced by charged particles, accelerated charged particles. We have seen various applications and various cases in which these sort of processes are relevant for astrophysics. Then we have studied quantum systems, and we have seen how to deal with transitions and quantum transitions within such a systems. And therefore, we have seen about emission lines, absorption lines, ionization, and all these sort of processes. After that, we looked at the connection between the Planck spectrum and the fact that there are absorption and emissions by atoms, as well as spontaneous emissions. And so we have basically proven that spontaneous emission actually exists and must exist to explain the nature of the Planck spectrum. Now that we have seen how we can see stuff, okay, through radiation, we are going to study how matter behaves, because we now know how a collection of particles, charged particles, are emitting. We know that also neutral particles are moving somehow according to their equation of motion, but we always dealt with the equation of motion of individual particles. We never seen how collective of particles behaves in general. And collective in particles in general are fluids or gases. Okay, so this is an ensemble of particles that are living together, that are interacting one with each other in a very efficient way. We will start with an approximation at the beginning by dealing with ideal gases and fluids. And then we will see how these objects are behaving. So we will be able to study the flow of rivers, of lakes, the fact that there are perturbations of waves on the seasides, and so on. We are going to see how the gas in this room is behaving, if we are going to blow air into it, for example. And that's the study of hydrodynamics. And of course, I just gave you terrestrial examples, just to give you something that is close to your experience. But you understand as well that with the same laws that we are going to derive now, we will be able to describe the very same matter that is filling the universe, such as the gas that is surrounding accreting matter around the black hole, forgetting about the part involving general relativity. We are going to be able to describe jets that are emitted by such black holes. You are going to understand how you can deal with structure formation across the cosmic universe, because as I said several times during these lectures, you see that there are initial inhomogeneities in the matter density distribution across the universe. Therefore, there are regions that are over-dense, and through their gravitational interaction, they are cooling under matter, and this structure grows until you have, from very tiny fluctuations in this, such a distribution, you're going to have very strong over-densities and under-densities, which over-density then culminate into the formation of stars and galaxies and this sort of stuff. And even over smaller scales, in the material that is accreting around stars, you can see how this matter is behaving, how it's flowing, and so on and so forth, to give rise then to the formation of planets, for instance. Similar mechanism, you can understand what is the formation of stars. Okay? So you see that now we are going to deal with a very powerful tool that is used a lot in basically most of the fields that you may be interested in when you are in the field of astrophysics, and cosmology as well. Because structure formation, if you wish, is also part of cosmology, because through the study of these formations of these gigantic structures, such as galaxies, galaxy clusters, you can get information about the overall cosmology, about the overall space-time of our universe. So in this case, it's going to be a tool. It's not the subject. In cosmology, it's a tool to study the cosmology. Okay, so let's see, first of all, what is a fluid. So as I said, it's a collection of particles. We can take a little chunk, small volumes, and what we basically identify is a typical length. Let's take a cube, so L, L, and L insides. That contains a lot of particles. So if you take the mean free path, lambda, that's on the order of 1 over the square root of so n to the minus 1/2. That's the number density of galaxies. Of particles. If you do the square root, so this is a 1 over, cubed actually, is a 1 over a volume. Therefore, with the inverse, the volume goes up. With the power of 1/3, you get the typical length. Okay? That's the typical separation between particles before you have a collision between the particles. This has to be way smaller with respect to the typical cube for which we want the properties of our fluids, meaning we want, if we are studying a river or the air in this room, we take a volume that is characterized by this LLL by side that contains a lot of particles, because what we want to derive are average properties, ensemble properties of the fluid. We are not interested anymore in the equation of motion in each individual particle because nobody cares. You want to know how a small volume is behaving in terms of perhaps thermal expansion, thermal contraction, motion, because you have or how it is twisting, and all these sort of things. Okay? So we are aiming at ensemble properties. Therefore, we want the chunk of volume that you have studied to be way larger than the typical collision length of the particles, between the collision between particles. And this as well must be much smaller than the typical size of your system. So let's take this room, okay? I don't want to have the big L like this room, because otherwise I make an average of everything. I don't know where the flow coming from the ventilation is going, because I'm averaging everything, so I'm destroying a lot of information. We want a small cube, characterized by this L, such that I can see how it is behaving. Okay? If there is wind, it's shifting somewhere. If I'm heating it up, for example, through radiation, then it's going to expand, right? And all these sort of processes. Therefore, I want this cube to be small, but still large enough to contain a decent number of particles, such that I can have a proper averaging process. Okay? If it's too small, the average is shaky. Okay? I'm going in the limit. If I make it very small, that it contains only one particle, that I'm studying the equation of motion of one particle, and I don't want that. Okay? So that's what a fluid is. We want to have, as I said, very efficient interactions. And in this case, we are talking about collisions. So in this model, you have really to think of gas like balls, okay, that are hitting one against each other. Then we are using a statistical approach. So the main tool that we are going to use, again, is the phase space, right, that we already encountered. And in particular, the distribution of these particles in the phase space. So if you have, now I take a slice, I remind you, it's this 6-dimensional space that contains all 3 spatial dimensions. And for example, now I'm making a cut through this x plane and the py plane, for instance. I could use pz or whatever, okay? And what we are going to describe is, for example, a fluid that is which particles which particles as described by this phase space distribution, is going to tell me what is the density of particles that have a certain position and a certain momentum. Position in all three dimensions and momentum in all three dimensions. If I now set the 0 here, and I have this density that is larger here in the middle, okay? Then is a little bit less outside, and even less, and then it vanishes to 0. This tells me that this is a clump of gas that is confined across the x, is located at this position along the x, and it is moving in the positive direction, on average, with respect to the y direction. You see that? It has a positive p. It means that it's moving with a certain velocity along the y direction. These particles that are here are moving slower with respect to the particles that are up here. Okay? They have a smaller momentum with respect to the particles that are up here. Okay? And as well, this phase space, as I described it, is confined in momentum. If we have a Maxwell and Boltzmann distribution, then we know that if I take the absolute value of the momentum, it goes to infinity, right? With the exponential tail. Okay? That's your phase space distribution and gives you the full description of your system as a collective of particles in a statistical fashion. You see, we are not tracing individual particles, we're just looking at averages already at this stage. Now, what we want to do is that, you see, I've also introduced a function of time because it might evolve. For example, it may evolve. Let's say that I have this clump of gas in a lower dense environment with a lower pressure, it will tend to expand. Let's say that if this guy is confined in a bottle, I can compress it, or I can expand it, or I can make a hole, and then it starts to flow out. Okay? And therefore, I have to introduce as well a time evolution because my system can evolve. Unless I am in equilibrium. In equilibrium, statistically, nothing is happening. But this is I'm using x and p. That's not very nice because I'm splitting space-time and I'm taking the space and the time apart. We don't want that. We want a theory which is covariant. And therefore, we want a function that depends on x mu and p mu. Okay? We are moving to the Minkowski space. To do that, let's start with the, let's say, the standard 3D, well, 6D non-covariant formalism. And you very well understand if I want to count the number of particles, so I want to know the total number of particles, I just have to integrate that distribution. So I just have the integral over the three-dimensional position, the integral over the three-dimensional momentum of my phase space distribution. And this must hold for all times, because I'm not creating particles, I'm not destroying particles. I don't destroy or I don't create particles here. See? N is constant, therefore it is invariant under any transformation because it is a constant just. Okay? So now let's try to make the same stuff but in a covariant fashion. Now my number of particles is going to be given by the integral over x to the power of 4. So I'm integrating as well over time. The integral of the cube p of this function x mu p mu. Then now is embedded in our four-dimensional space, where it's actually 4 times 4. Okay? And you see that now the time dependency is swallowed by our x0 component, because that's the guy, the component that it refers to time. Now, we have that n is invariant. The cube x and the, sorry, to the power of 4 and to the power of 4, so the volumes in space and position are invariant, are Lorentz invariant. And because it's just a constant, is the number of particles that I have there, so it cannot change. It's just a scalar. These guys are the volumes of the x and the p space. And they are invariant because the Lorentz transformation have norm 1. Okay? So the volume is changing shape, but it's not changing volume. So the cube, right? That's the volume of the in that space. Then we want particles to behave as real particles. Therefore, they must obey the rules and the laws that we have seen for the particles that we studied so far. By the way, this goes for minus infinite, infinite, minus infinite, and infinite. Good. So which kind of constraints do we have? Number one, we know that the energy, that is defined as Cp0, is equal to c squared p squared plus m squared c to the power of 4. This set us a constraint. You see this is a constant. Then we have the momentum and the energy that are locked, one with respect to each other. Okay? So this is a constraint that we must impose to our equation. Therefore, we have that p0 power of 2 must be equal to p squared plus m squared c squared. Right? You see the momentum is locked with respect. So the three-dimensional momentum is related to the zeroth momentum. Then we have the constraint number 2. The energy of such a particle is related to its kinetic energy and can only be positive. 0, if it is not moving, we are in the rest of our particle. Otherwise, it must be positive. Energy is positive. Let's now impose our constraints in our distribution. So we have the integral between minus infinite and infinite of the to the power of 4x. Then the momentum must be larger than 0 for the 0th component. So I'm splitting this integral of an integral of an integral of an integral 4 times in two components, between 0 and infinite for the dp0. And then I have the other three components that are free, between minus infinite and infinite, because the particle can move, have a velocity in any arbitrary direction, dp cube. Okay, you see this integral here is this guy here, where the 0th component goes from 0 to infinite because I imposed this constraint. Then we have our phase space function. And then I have to apply this constraint through a delta function. So I want that p 0 squared minus p squared. This is not a minus, this is a bar. That's the vector, of course. Plus m squared c to the power of 2. Right, you see? This guy is equal to 1 only when this is equal to 0, which is exactly this equation. Okay? Then I have this integral with respect to the component 0, and as a variable here I have p0. I can exploit one of the properties of the delta function, meaning that the delta function of a symmetry like that, where the variable is this one, minus its root, because you see this is the root of an equation, divided the derivative of the function that is contained into here itself, gives you that. So we have the integral, it is minus infinite and infinite for x. Then I'm letting this guy for the moment here. I let it act afterward. And then this one as well, yes. Let's put this. Front 3, 0, 0. So I just flipped these two, nothing more than that. Then we have the x mu, p mu. And then I exploit this property of the delta function. So this is just a mathematical trick, okay? In the notes, there is the derivation of how you do that. But it's just one of the properties of the delta function. It's just, there's no physics there. It's just a mathematical trick. Then we let the delta function act. You see, these are integrating over delta d. What is it doing? It's going to select the p0 component that represents the energy. You see, this is the energy for our particle. They give us the c that I bring in front of all integrals, because it is just a constant. Then we have the integral of over all the x volume. Then we have the integral 3D of the momentum over 2e, that are these guys here. Then we have the phase space distribution, x mu, but with the constraints. That is coming from the delta function. So this is, you see, this is my p mu. There is the p0 and the vector p, where the 0 component must be the energy of the particle that is given by this constraint. And then we have the three-dimensional component. Okay? Good. Okay. And then I need to introduce this function as well, because this guy, this function here, p0, must be equal to 1 or to 0 in the case of p0 larger than 0 or equal to 0, or p0 equal to 0. And that's needed to keep this constraint living. Okay? What do we have? We have that n is invariant, this is invariant, this is going to be invariant as well, and this is going to be invariant as well. Lorentz invariant. Okay? So here you see the constraint that we had to impose to so the only part of physics that you see here is the understanding of this phase space distribution. I think it's clear by now. It's just the number density of particles in the phase space. Therefore, it tells you what is how many particles do you have at a certain position with a certain momentum. We moved from our space and time separate to something that is implemented in a covariant application in which everything is based on x mu and p mu. So we are using the space-time in the Minkowski space in this case. And then we just impose these two conditions, namely there is a link between the p0 component and the three-dimensional component of the momentum, because we must obey to the energy properties of particles, of individual particles. As well, we have two, this should be a point 2, actually, not 1. As well, we need to respect the fact that the energy of the particle can only be positive. Then what we used is just a trick for the delta functions, nothing more than that. And we arrived at these final results, where we have also the conclusion that this guy here must be invariant. As it should, because we started with two invariant integrals, volumes, and this guy is kind of inherit that property. Let's try now to construct a fork current in analogy of what we did with electrodynamics. Remember that in electrodynamics we defined this fork current, which was capturing the charge density where ρ has to be intended as the charge density. Then we have the three-dimensional current, the standard three-dimensional current. It's equal to C. So we want to arrive at the end at something like this. Rho, yes, because that's already a density. Where we had rho charge density, and then we have v, which is just the standard velocity, or if you wish, j vector is the current, 3D current. Okay, that's what we had in electrodynamics. Now what we want to do is to describe something similar, but for charged particles. Therefore, we are moving from a charge density to a matter density. And before arriving at that, we first have a stop and look at a number density. Okay? So we will first derive a number density to arrive as a final goal matter density for our fluid, which is amount of kilogram per cubic meters. So let's start with something that is related to the number of particles. For we define a J0 as the number of particles. Simple as that. That is, as we have seen, related to the integral, the cube P of the phase space. Now I'm using this guy here. You see, if I make the integral over the momentum, I'm leaving apart the integral over the three-dimensional volume, which means that this is a density. Whenever I integrate a number density with respect to the volume, I get the number of particles. Then what I do, I just, because you see, I'm trying to arrive at a 4 vector, so I need to introduce a component for the 0. So what I do, I multiply times the 0th component of the momentum, and I divide with the 0th component of the momentum. I haven't done anything. But I can now plug into here its relationship with the energy, because we know that P0 is equal to E over C. And therefore, I have this expression, the cube P over E. So the C, I brought it. This is P0 over this guy. So the C goes on top. The E goes below. Then we have the integral of the phase space. Sorry, we have the phase space density, P0. And now why I made all this fuss about this stuff to arrive at the thing that is invariant? Because now this is invariant. You see? So I made this machinery to arrive at something that is the component of a vector. So I'm relating J0 with the 4 vector, which is what? Which is a vector in the Minkowski space. So it's a covariant vector. Let's now use the machinery that I built here for the 0 component, and let's just make it general for the other 3 components, 1, 2, and 3. And I just use the definition that I have up there. So the cube P over E, f of x P T, P E. Same structure. Such a way that I have one mathematical object that describes in a coherent way all 3 components. Then in this case, I'm now linking. You see, I want to arrive at something that has a velocity. So I am linking the momentum to the definition of the velocity and the energy of my particle. And I have that PV. We have seen this when we did relativistic mechanics. So the momentum of a particle is E over C squared V. I'm going to use only the E component, and I'm not going to call it V, but I'm going to call it V dot. That's because now I want to distinguish between the motion of one individual particle, x, and V, which is going to be, in the end, the velocity of my fluid. Okay? So we plug our relationship into here. So we have C integral of the cube P over E, Fx P time. So I haven't done anything. Now I plug in my definition, E over C squared x dot component E. I'm using only the E component. Energy, energy, C, and C. It becomes 1. Then look, I have a density of particles integrated over the full momentum P times this x dot. I can relate this guy here to the average of x dot. How? Well, it's very simple. I just multiply this guy by the integral over the momentum, 3 dimension, and then our distribution. and I divide by the very same stuff. You see? I arrived at this result. Then I multiply by that, and I divide by the same. So again, I haven't done anything. But if I group this function here, and I leave this guy on its own, what do I have? I have that this guy is actually n position and time. See, I'm making the integral with respect to the momentum. I'm left with the number density at the position x and t because I integrated over the momentum. And what is this guy here? Well, that's actually the definition of the average of the only function that is left inside, which is this x dot. Okay? I have the 1 over c. I can bring it outside. Then I have the average of x dot component e. And again, this is at the position x at the time t. Time the number density at position x and time t. Okay? I will drop this x and t. So, what is this c? There is no c here. Okay? I will drop this all this stuff here, and I will just leave it like that. Okay? But keep in mind that this is for a certain position at a certain time. And look what I've done it. Now we have an ensemble property for our fluid, which is the velocity. You see? This is an ensemble property because it went through an average, so the property contains the properties of each individual particle, velocity x, component e, for an ensemble, for an average over a certain volume in the momentum space. For I define the velocity of my particle, well, that's for the component, 1, 2, and 3, so it's valid for all of the 3 components. This is the velocity of the fluid. And this is the velocity of the particles, or of each individual particle that we are going to average. Let's see now if this definition that we constructed holds, and if it gives us the conservation of the number of particles. Because we started by imposing conservation of the number of particles. We have now this for current density. Let's see if it obeys the continuity equation. Which is that one. And J, again, is not referring to the current density that we have seen in electrodynamics, but is referring to the number density, so the current of the number density, N. So what we need to do to see if everything works, we just need to plug in our J mu into here. That's it. Okay? So let's just write J mu in all its beauty. So that's equal to n xt over c and v. Okay? C and C drops. We are left with nxt, which is what we have in first place. And then we have n over c times the velocity of the fluid, which is exactly what we have here. Okay? Let me write it. This guy is our VE, all of it. Let's now plug it in. What we have? We just have to apply this operator, that's the derivative. You see I have mu and mu, repeated index up and down, so I have to apply my Einstein summation. So I have d over c dt, that's the zeroth component of my delta mu, times nxt, the c and c drops, right? So that's the zeroth component, plus delta j, so the 1, 2, and 3 components. Now I leave it in, I leave it in the Einstein formation, the Einstein summation explicit. 1 over c n x t v component j equal to 0. C and C disappears. And yeah, it does look like the continuity equation. So we have the t n x t plus the j n v j. Write it like this. N plus the j n v j. If I want to write it for all components, the t n plus the gradient of n. See, there is the scalar product here, as I have a scalar product here. This is the continuity equation, and it expresses matter conservation. Now look what we can do furthermore. If I now multiply this guy by the mass of each individual particle, I have number density times mass. This is going to be a matter density. This guy is 1 over meter cubed. This guy are just kilograms. Therefore, this function here has units of kilograms over m to the power of 10. Therefore, I can write this guy here as T rho plus the gradient of rho equal to 0. Nice. Now we can have a break. We can reconvey at 15 past 10, and we will continue with the derivation of the energy momentum tensor, because what we have seen from the previous lecture is that that guy is the thing describing the system that is conserved. And by imposing energy momentum conservation, or by exploiting the energy momentum conservation, we will be able to derive the equation of motion of our system, therefore of our fluid. Okay, so it's 15 plus 10.